What's up, guys? It's me, Sir Ernest, and today we're going to solve problem 8.12 of Fowles and Cassiday 7th edition. The problem reads, a uniform solid ball has a few turns of light string wound around it. If the end of the string is held steady and the ball is allowed to fall under gravity, what is the acceleration of the center of the ball? Assume that the string remains vertical. So we first set up our coordinate axis. So let's say that the vertical direction is our y-axis. So therefore, anything that's pointed downward will be negative, and anything that is pointing upward would be positive. So just like any mechanical problem, we first identify the forces acting on this object. So here we know that gravity acts on it, and that is Fg. And this is equal to m times g, where g vector is negative g j hat. Also, along the string, there is tension. So the tension on the string is upward. The gravitational force acts on the center of mass of the object, and while this object falls down, it rotates in this direction. And here, A is the radius of your ball. Since this object undergoes both translation and rotation, we can express the motion in terms of their equations of motion using Newton's laws of motion. Here, for translation, the equation of motion will start with T plus Fg, and this is equal to ma. Because the object is falling down, therefore, the acceleration, which is y double dot, is directed downward. So therefore, we can rewrite this as follows. T minus mg equals negative m y double dot. And this y double dot is the acceleration of the center of mass. For rotation, we know that the net torque acting on the object is equal to the product between the tension and the radius of your ball, A. And by Newton's second law for rotation, this is equal to the moment of inertia about your axis of rotation. So in this case, let's call that z-axis. If this direction is x, therefore the axis of rotation is about the z direction. And we multiply this with the angular acceleration omega dot. So in this case, the moment of inertia about the z-axis for this solid ball is equal to 2/5 ma squared, where m is the mass of your ball. So combining these two equations together, we now have mg minus my double dot cm times a, and this is equal to 2/5 ma squared omega dot. Simplifying this, we now have g minus ycm double dot. This is equal to 2/5 a omega dot. Since a omega dot is equal to ycm double dot, therefore g minus y double dot cm is equal to 2/5 y double dot cm. This gives us the final result where the acceleration of the center mass of the ball is equal to 5/7 g. So as you will notice here that the acceleration is less than the acceleration due to gravity. So if we're going to have another ball that will be allowed to fall at the same time as this ball, that ball in free fall will arrive first on the ground than this ball that is attached on your string. So that's it. That's the solution to problem 8.12 of Fowles and Cassiday 7th edition. I hope you learned something today. Thank you guys for watching, and I'll see you in the next video. Bye-bye.